I would consider several algorithms, several concrete algorithms for quantum computing. Yes, so namely it would be Grover and quantum Fourier transform. And if I have time, then I would also go some application of quantum Fourier transform to other problems, which would be the preparation to the next lecture. I think the next lecture will be once again with a blackboard, because I would explain some complicated algorithm. So, and then I prefer to do it slowly, but on a blackboard, yes? So, first of all, there were exercises from previous lecture. Do you have maybe questions which you? So there was somebody who wrote to me with his ideas. Yes, some problems were solved, some problems were not solved. Yes, so I encourage everybody to do this. Yes, so once again, my email is this one. Or the same IMPA, Gmail or IMPA, so feel free. Yes, this is not only to you, but also to the audience on YouTube, which is much bigger than here. Yes, so I'm going to speak about quantum search. So this is actually one of the two famous algorithms. So the most two famous is Grover and Shor. Yes, and this is Grover's algorithm of quantum search. And let me explain what does it mean when in quantum computers we say quantum search. Yes, so setting of a problem. Assume that we have a function which is like goes from integers to 0 and 1, and it is 0 everywhere except 1 of the values, and 1 in this particular value, yes? So, and you can run it with a number and get a result, 0 or 1, yes? You're looking for Sarah Connor, yes? So you can go to Sarah Connor by telephone directory and check if this is a Sarah Connor or not, yes? So this is what is happening. And okay, what we want to find this x, this t, this value for which it is 1. Yes, we want to get this in the computer somehow. Presuming that we know this function is a black box, so we can run it, but we don't have knowledge about what is t there. Yes, so this is the setting of the problem. Yes, so like all the search algorithms can be actually reduced to this one. Yes, and if we do on a classical computer, what we can do, we can only try one value after another. Yes, and if those values are between 0 and capital N, yes, then we have to, from 1 to capital N, we just need to try all of them, and unless we get 1. Yes, and typically, for this, we will need n over 2 numbers of run, yes, until we reach 1, yes, so unless we guess, yes, and okay, this is capital O of n, yes, and this is capital O of n running of this black box function, yes, so this would be, so we would have several measures of complexity, so how many gates or operations we need to do, which created by ourselves, and how many runs of this black box function we need, yes? So I will pay attention to both bracket notation with these fancy symbols like this, yes, it's a matrix, yes, so I can technically do this, but let me tell how it actually works, yes? So it works as follows, so it's identity on all the basic states which are not t, and it's minus minus for x equal to t. Yes, so that's how it works on a basic states. Yes, on a pure states. Yes, so then, okay, I could consider this as a definition of my operator. How I can get it, this is question for later. Assume that I have it, yes, but I don't know t. Yes, so I can implement, I can run such an operation on a quantum computer, but I don't know t. And my goal is to find t. Yes? Once again. So the idea of, so I will need also one more thing. And so I will need S, some initial state, to which I know how to put my system. And I need some operator U with the following properties. So if I can see the scalar product between T and U applied to S, then it would be not 0. And the second thing, I should know this value. Yes, so they are not orthogonal, and I should know this value. Yes, for algorithm which for Grover algorithm, I don't need such a generality. Yes, I just can use a particular S, which would be 0, and a particular U, which is just Hadamard gate applied to every qubit. Yes, because then what is, as we learned before, if we apply Hadamard gate to 0 initial data, then we will get just sum of all pure states, okay, normalized by a proper value. And here it is important by which proper value it is normalized. Yes, so it is 1 over 2 to the power n, where n is number of qubits. Yes, and the scalar product between those guys for any t will be the same. It will be this 1 over square root of 2 to the power n. Because if t is equal to x, then it is, this scalar product is 1, and we have this normalized coefficient. And if t is not equal to x, then the scalar product is 0, because they are orthogonal. Yes, so this is the value there. Yes? So if you see, if something is wrong with the notation, if you need additional comments, yes, please feel free to stop me. Yes, because I spent with these guys quite a while, and for me, all this notation is clear. And we played a lot with notation during the Deutsche-Jose algorithm, yes, but might be it is not enough. Yes, might be you want to ask more, and I would be happy to answer.
Okay, so my first question would be the first equation, because
The?
we were presented the bra, it's cat bra, not bra.
Yeah, no, because bracket gives you a number, yes, because it is a line multiplied by a vector, a line multiplied by a column, yes. So what is T? Yes, it's a column of complex numbers. Yes, what is bra? Yes, it is a row. Yes. Yes, it is row. Yes, and if I multiply, so there what I should do, I should multiply column by a row. Yes, and this is a matrix. Yes, so like technically it is but it doesn't matter. So I quite often use word technically, yes, which confuses Charles. Yes, the reason is that okay, I use here completely correct mathematical notation. So and if you're a mathematical freak and would like to follow what I'm writing here, everything is completely correct. Yes, but if you want just to apply this to computer, the notation might be confusing for you. Yes, because it's much easier to look on the operator as it's written here. Yes, but then I need to define. Let me consider operator, which is on the basis define it like this, while I can simply write it in one line. Yes, and another thing is that more complicated becomes algorithms. Yes, more notation like this you have to use in order to understand them. So I'm slowly introducing it. This is basically what is happening, yes? Because I can say, come on, you don't know how to multiply line by a vector, or vector by a line. Of course, you know, and you can become shy, yes, that you cannot do this, yes. But I prefer not to make you shy, yes, not to make you confused, but better slowly introduce, because at some point, the algorithms becomes enough complicated, so without notation, it's not possible to follow them at all, yes? So this is why I need this step by step, yes? And how to say, this is, okay, if you want to understand algorithm now, it's better to follow this thing, but you should remember that this notation is also possible. And moreover, I can write it like this, and I can start to open bracket, you know, have several operators, and start to do manipulation similar, like classical manipulation, which we are doing with vectors, matrices, and so on, and I would be correct. Yes, so this is why it is. So this is why it is useful. Yes. Okay. So more questions? Okay, so I fix S and I fix U like this, and I know this scalar product. And this scalar product should be a number, yes, and I know this number. Yes, so now first I will tell what exactly Grover algorithm looks like. At this moment, it is okay, it's normal that you don't understand why it is working, so we will understand this the next slide. Yes. So, okay, I assume that I don't have, I have not only this black box IT, but I assume that I also have an implementation of not black box, but white box IS. So this is my job to implement IS. Yes, but S I know, and it's a similar thing. We just invert sign of one of the of one of the elements of the basis, and this element is 0. Yes, okay, I need to implement it, yes. By the way, unfortunately, if you are working with n, where n is large qubits, then you will have to use control not there, and we remember from the previous lecture that it is not so trivial, yes, to implement it. But still, it is possible to be done, yes. And one tricky thing that, of course, because we need control not there inside. So if we don't use ancilla qubits, then it is exponentially big. And so this becomes capital O of n complexity just to run this guy, yes. So we have to use ancilla qubits in order to run this properly in a faster time. Yes, so because our goal is not just to construct an algorithm, our goal is, to be faster than classical algorithm. Yes, and okay, in this case, let me consider operator Q, which I can define it as the following. So I first apply IT. After this, I apply inverse of U. I apply this ES, after this I apply U, and okay, I change sign. I mean, this doesn't change the state, but it is like convenient in order to have something. And to prove, yes, in real computation I actually will not. So I show how one can run this on a quantum computer. I will not put this minus. Yes, and let me draw a scheme how it is. Yes, so I have here several qubits. So I first do this IT, which is a black box. Yes, and I don't know how it is implemented. After this, I use U inverse. Okay, in my case, U was Hadamard operators. Yes, so inverse to Hadamard operator is Hadamard operator. So I just put H's here. After this, I put IS, which is implemented by me. It's not a black box. So this is black box. And this is my implementation. And after this, I do once again H. And I especially, why I draw this, yes, why I spend time on this. Just to pay your attention that, remember, yes, so if you have to write here a state, yes, it would be written here, but it would be applicable from the right to the left. Yes, so when you copy such expression to a scheme, you need to revert them. Yes, so please, I mean, this is very easy to make this mistake, and after this, your program on the quantum computer doesn't know that you made this mistake, so it does something not correctly, yes, and so on. But after this, what is I suggest to do? I suggest to start with S, so which was all zeros. So apply U to it, yes, once again, and apply operator Q, which is now a big operator, yes, big operator, several times. And the number of times I wrote here. Yes, okay, we should remember that n is 2 to the power small n, yes, but it's not all, square root of it does not always exist, yes, so I mean not always an integer number. But in any case, we multiply on some crazy constant p over 4. So in any case, we should not expect this to be integer. Yes, we would take the integer the closest to it. Yes, not necessarily smaller or bigger, just something which is close to it, in fact. This is enough. And okay, after this we can measure, yes, all the qubits, yes, and with high probability we will get T. Yes, and let me yeah. And up to now it should be a bit a miracle why it works, yes, but let me explain why it works. And I would explain it with a blackboard more than with slides, so please just use slides for reference, not for true explanation. So let us see, yes, once again, how the operator IT works. Yes, it was diagonal operator where everywhere is 0 except one of the places. Yes, but let us, but this is a reflection. The same thing is with IS, so it is a reflection with respect to another vector, yes, S. But here I wrote U inverse U, yes, which means that I just changed the basis. So it becomes actually a reflection with respect to a hyperplane orthogonal to U of S. Yes, and now what I have T, I have U of S. It is not a basis vector, so it's much more complicated object, yes? But still, what I'm doing rotation with respect to a hyperplane orthogonal to it. And now we remember high school geometry. Yes, composition of two reflections is rotation. Yes, and it becomes a rotation in the plane which is a linear, which is based on these two vectors, US and T. And this is a rotation on angle with this formula, yes, where alpha is the angle between the original vectors. Yes, and okay, let me amend this high school business, yes. And okay, what I want you to remember is that composition of two reflections is rotation. Yes, but to which angle, please just believe me. Yes. And okay, so this means that each time we are doing a rotation of a vector by this angle, and okay, alpha is actually very close to pi over 2, so to small angle each time. Yes, and what's happening? So each time, so we started from this vector, yes, because we start to apply this q to us. Yes, so we start from this vector and we do rotations here, yes, some theta, and if we know this angle, yes, which is actually alpha, yes, and we know the angle on which we rotate, yeah, which is 2 pi half minus alpha, then we know how many iterations we actually need to do, yes, in order to get to t. Yes, and if the ratio between alpha and theta is not integer, we just took something close to alpha divided by theta, and got some, and in the end we'll get some vector very close to t. Yes. And okay, so let us do these calculations properly, because okay, we know that actually the scalar product which I wanted to know in the beginning is just cosinus of the angle. Because this was a small number, 1 over 2 to the power and half, yes, so it's similar then, okay, cosinus is the same as sinus of proper angle, and sinus of a small angle is approximately the same as the angle itself. Yes, so I have to use this. And so after k iterations, we do rotation approximately to this angle, and so, okay, let us see, okay, so let us choose k of this form, so, and I say it, okay, alpha is approximately pi over 2, and pi over 2 minus alpha is approximately the scalar product which I knew, and I properly calculate everything and get exactly p over 4 square root of n. So actually, it's more correct to consider this number, yes, to p over 4 square root of 2 to the power n. Yes, and then you know, we would be very close to t as a geometrical object, and then when we measure, we would get t with high probability, because kind of this is with high probability projection would be on t. Yes, when we consider proper self-adjoint operator for measurement. Yes, so this is why it works on geometrical meaning. Yes, so please, you know, if you're confused, ask me questions. Yes, because.
Like a problem of optimization that we are iterating in each step, but I don't know, it's not clear for me what the value that we are estimating and how we measure how much we missed to better.
So okay, so here I didn't. So there are two elements. Yes. First of all, that, okay, this rotation in a geometrical space is happening, yes, and you believe in this, yes. You know that original angle was alpha, the final angle is, the angle of rotation is theta, yes, and you, okay, we cannot do exactly alpha divided by theta iterations, yes, because it is not an integer number, yes. So then you're asking, okay, if we did not exactly this, yes. So with which probability we will get exactly t?
Okay, I think I'm getting it. Like the error is like the alpha over theta. If I might.
Yeah, no, the maximum error is theta.
Okay.
It's actually theta divided by 2, yes? But okay, maximum error is theta, yes? Then with the probability more than more than cosinus theta, yes, theta is almost 0, yes, so more than cosinus theta, you will get exact t. Yes, so probability to get t will be at least cosinus theta. And cosinus theta, okay, it's something of order 1 minus 1 minus 2, 1 minus 1 over t to the power and half, yes? So might be here I should put a coefficient, let me be. So to not confuse you, let me necessarily put here 2, yes? I don't remember exact constant. But it is important that probability is bigger than 1/2, because now we use square root of n iterations, and if the probability is bigger than 1/2, so then we stay with the same complexity class. Okay, in average we will need might be 2 square root of n operations, 4 square root of n operations, yes, but something of order square root of n, yes, which is now how to say, quadratically faster than original algorithm. So here we don't get exponential speed up, yes, but we get quadratic speed up, yes, which is also an interesting story. Yes, it doesn't help you p equal to np, yes, but it helps you to speed up real algorithms. Yes, and okay, so if you are not happy with the geometrical story, yes, you can repeat the same in algebraical sense, yes. And the key idea here, let me mention it a bit, is that, okay, the hyperplane, which is generated by vectors us and t, remains invariant. So you can write everything inside this hyperplane. And if you write everything inside this hyperplane, okay, you can explicitly write all the operators as a 2x2 matrices inside this hyperplane. Yes, and okay, you can use, I expect that, you know, whatever you do with 2x2 operators, you're able to do this. Yes. So, okay, there is a way to check that q to the power k would behave properly. Yes, in that case. Yes, but I will omit because, you know, this is just calculation. This course not about such calculation. This course is to understanding the mechanics of quantum algorithms. Yes, and just important tool that yes, you have a two-dimensional hyperplane which is invariant, so you always stay inside it. So you can write all your evolution, yes, of the state inside this hyperplane, and to work in this basis. Yes, basically, remember that S was unitary. So US is also unitary, but they are not orthogonal. Yes, they are not orthogonal, so this is this is not orthogonal basis. Yes, so you should not expect that some properties or coefficients of matrix because of this. But you are allowed to do this because this is valid mathematical tool, and you know we use the abstraction that the state of quantum computer is just a complex vector, is a vector in a complex linear space. So that's it. A few more things, yes. So if you run, okay, what's happening if you choose not proper number of iterations? Yes, I don't know why, but if you do this, so this is the probability of success depending on number of iterations of Q which you are doing for some operator, yes, for some number of qubits. Yeah, so you see it's increasing. There is a peak where kind of it doesn't matter plus minus 1, 2 iterations. You still get with a very high probability the proper result. But after this, if you do more iterations, the probability decreases actually almost to 0. And increases once again. And this is natural because if you have a vector rotating, so then it goes periodically, yes? Is it close to t or not? Yes, and this is what is happening. And let me first show how it works, yes? And after this, I show some extra information, yes? So here is my implementation of ET. So this is just for one of them. Yes, and this is implementation of ES. Yes, and let me pay attention on how, so you look on this scheme and might be not understand anything. Yes. Let me look onto the scheme and explain how to get it. So S was equal to 0. Yes, and if I want to have ES, its matrix is minus 1, 1, 1, 1. And then the rest are zeros. How I can get this? Yes, so there is, first of all, you need an idea, and the idea is the following. Let us consider let us remember that there is a Z operator, which was 1, 0, 0, minus 1. Then, let us see how it would act as a control Z. Yes, as a control Z, it would do 1, 1, and you should put matrix Z here, so 1, minus 1. Aha! It has almost the same structure, yes? The only thing that minus 1 is not in a proper position, yes? So our goal becomes to change basis, yes, so that the vector 1, 1 becomes 0, 0. Yes, you should do some operators, yes, you can, so you can do everything, like anything, A control Z, A minus 1, yes, and they choose as an A operator which would moves this here on, and it cannot be arbitrary operator because it should put it should leave the poor state as a poor state. Yes, so there are two restrictions. Yes, it should do like this and move x to y. Yes, so it cannot mix states. Yes, and the easy implementation of such A is just 2 nodes. Yes, because it leaves a poor state as a poor state. Yes, it moves 1, 1 to 0, 0. Yes, and its inverse, it's itself. Yes, so then this becomes a proper operator. Yes, so here I choose once again idea of change of the basis. So yes, it was chosen, it was used a lot in Grover. Yes, when I told that this is a rotation with respect to US. Yes, it's a reflection with respect to US. Yes, so this is the place where I use this, and here once again I use it in the place when I construct an operator. Yes, so now I choose IT as a sum operator. So and this is how control Z is shown in IBM. And let me explain why. Yes, because typically, as we seen, yes, you have when we write controlled something, it is like this. Yes, and you should expect that it is like this. The feature here is that this is equivalent to that. So those two schemes are equivalent, in fact. Yes. And it's easy to see from here. Yes, because this operator, what it should do, it should put here 1, 1, and here 1 minus 1. And this operator, what it should do, it should consider here put identity operator, yes, and here put z operator, because this is just a change, reordering, yes, when we switch them. But by the way, so both of them will give the same result, yes, so they are equivalent. So because of this, there is no reason to say who of them is controlling and who of them is implementing z. Yes, so because of this, they use this strange notation. Yeah, question? No? Okay, yeah, so then, okay, after I did this, yes, so this, I think this is for, so Control Z is for 1, 1, and this I changed, so this is kind of t is equal to 0, 1. Yes. Yes, and let me, so okay, U would be Hadamard operators, and so we have the scheme like this. And this is actually one iteration. Yes, this is, if you do calculations, then they will suggest you to do one iteration. Yes, and then, okay, it works. So this is the scheme for 1. But you can do 4 iterations as well, because you remember this sinusoidal thing. Yes, so you can do 4 operations as well. It also should work. Yes. And let me show how it looks like on a quantum computer. And I would have a reason to show it, not to leave it like this, so please pay a bit attention. Yes? So this is my implementation in of Grover. Can you see it? Yeah, okay. So it's implementation of Grover, the same as I put it on a previous slide. Yes, and okay, now assume that you want to do more iterations. Yes, more operator Q there. You should copy them, you know, it's not a convenient story. Yes, so because of this, they actually have some language. Yes, so you can introduce a new gate. Yes, so in the say gate Q, yes, so no, just so say I can implement gate special iter, yes, which is written on the same language as just if I put it on a scheme, yes, so and I can implement ES, and I can implement everything which I want. Yes, so here I don't know why I name it Q, I should name it U. Yes, so that's a problem. Yes, so then you see I can do just one iteration of Grover and call it, give it some number, some name, yes, and after this I can write code the same style as we do in a classical software development. Yes? Yeah?
I'm missing the old assembly of classical. Like, is there a go-to, a conditional?
No. Here it's not, okay, of course it's a limited language. Yes, so still, but you can, okay, let me say that you can define gates, yes, and okay, then it works. Yes, it has more possibilities, but let me not go deep in this because, you know, how to say, actually, first of all, proper way to learn languages is not by lectures. Yes, it's more by exercises. And the other thing is just to pay your attention, yes, to the fact that here there is some language which has some power. Yes. So because of this, of course, now it's much more readable. Yes. So I just first of all I apply two Adamars, and after this I do this one iteration of Grover. Yes, and I do it as many times as I need. Yes, and okay, I don't remember. I think I don't remember in this language, but there is another Qiskit which is Python based. There you of course can do cycles, ifs, whiles, everything. Yes, this is just a part of Python. You can think. Yes, here I don't remember what exactly you can do and what you cannot do. Yes, so this don't know. This is good for illustration because you don't have a lot things around. Yes, so you just can concentrate on schemes. Yes.
I'll just change my question because I'm afraid that in Python the algorithm will. Is there a way to write a quantum go-to with one?
No, of course. Look, of course, like in principle, it should not be like this, because there should be no go-to, because the quantum computer works with a different paradigm. So you set up a scheme and you run it, yes, and get a result. This is what you can do inside a scheme. You cannot do things actually, yes. So this is the problem. Yes, a bit. Okay, I showed this semi-classical control. So when you measure and depending on this, you run certain gates, but you should consider this as a interaction with classical. Yes, so you measure, you go back to your Python, yes, and you run next scheme. Okay, starting from the state in which you go. Yes, but by the way, I don't think that now such things working correctly. Yes, this is not because you see they're still in a position that measuring and setting up zero, it's better to use as a special, operation, not to separate this as two because of the quality of the result. Yes, so that's so. But I cannot answer to your question in complete way. Yes, so the idea that you can introduce new gates as a composition of existing gates, and this is quite useful. Yes, especially if you try to, Grover, you can just do copy paste, copy paste, copy paste. Yes, but as soon as you do something more complicated, say a shor, which we will not touch, yes, then it becomes a nightmare already. Yes, so let me finish with Grover, and after this we will have a break. Yes, and so there are a few things missing. Yes, so one of the things is how to make this operation IT from the Oracle. Yes, because we define it Oracle in a different way. But this we already did in certain sense in Deutsche User. Yes, you just create this second qubit in a state 0 minus 1. Yes, and after this kind of apply this Oracle, and you will get exactly IT there. Yes, so the same way as it was in Deutsche User. So you just need to set up this into state 0 minus 1. Normalized, yes, and then apply a quantum oracle. Yes, so this is the complexity is the same. Okay, but you need an ancilla qubit. So this is the feature. So another thing, yes. So there is a possible generalization of this thing, which is called amplitude amplification. That's for me, this is phonetically difficult. Yes, so the idea is the following. So everything what you need just to apply this idea is to know this scalar product. Yes, and as soon as you know it, yes, then you can repeat the same story. You not necessarily take U the same as I did. You not necessarily take S the same as I did. Yes, you can choose your favorite values. The only thing which you need to know is this property. And the true reason is that, okay, Grover is nice, but of course it's a bit artificial. Yes, it's a playground. But one of the things where a quantum computer can help is a simulation of Markov chain Monte Carlo. Yes, and it's a good idea to do this because of the two things. So one of the things is that because in the end you do measurement, which by itself is a good good source of randomness. Yes, so and another thing that, okay, you might choose complicated algorithms, yes, so which is Markov chain Monte Carlo. So when you have some Markov chain and you want to do a sampling by the invariant measure of this Markov chain. Yes, and doing sampling is a very good idea, and it's a good idea to put it in a quantum computer. You can do this not only to Markov chain Monte Carlo, but say to Bayesian sampling. So when you do Bayesian Bayesian, I don't know how it's in English, and but then, okay, you will do the same idea with operator Q, with choosing proper number of iterations, with rotation on a space, but with different T. Now T will be not a pure state, it will be the invariant measure of your Markov chain. So the S will be invariant state of another Markov chain, yes, and how to say, there is some work to be done there, but it is possible. This is one of the possible applications in which I believe. Yes, so it's possible to do because you do randomness, yes, and you make it speed up. It doesn't allow you to go outside of the exponential class. Yes, so this is the problem that Markov chain Monte Carlo has very long time to converge. But here it's possible to do quadratic speed up, which is also a lot. Yes. So this is one of the things. And another thing that I presume that you don't have just one value for where this answer is true, but you have several values. Yes. So T correct answers. Yes. Then you can repeat the same idea. You just need to use another number of iterations. Yes. And here I wrote what it is. Yes. And instead of S and T as we used, you should use psi good and psi bad. So which is how to say, the good vectors is the correct answers and bad vectors is not correct answers. Yes, and to write everything in this basis. Yes. So it would be similar to this diagram, yes, but the peaks will be in other places. Because you see, everything depends on an angle. Yes, and because what I did, yes, here, yes, I used here the T is just 1. Yes, assume that now I consider instead of T, I consider this what I call psi good. Yes, so several. The combination of several states with the same coefficient. Yes, so now I have this coefficient. I have so a US. Yes, was 1 over 2 to the square root of 2 to the power n sum of k. Yes, now psi good. Yes, is 1 over square root of t sum of some j's, yes, and this is j in some set of length t, yes, and if I consider this scalar product now, yes, so then I will get t non-zero values which should be multiplied on proper coefficients. Yes, and I summate them. So I still know the scalar product. Yes, and I still can repeat the same idea. Yes, but now, okay, I will come close to this vector, not to that vector. Yes, and so when I measure, if I was close to this one, with high probability, I will get one of those. I cannot say which one. Yes, but my goal is to find at least one. Okay, yes, I got. Yes, so my goal is to find at least one vector of them, not all of them. Yes, and this here you're correct. Yes. Okay, I got your question. Yes, now. Yeah. And okay, so I think, yeah, that's it. So let's have a break. 1, 2, 3. So let's go to the next algorithm, which is quantum Fourier transform. And by the way, I believe that this is a huge and powerful tool. Yes, first of all, because all of us as mathematicians have heard Fourier transform, and this is important feature there. The second thing, it allows to have exponential speed up to it, yes, by itself. And it is a relatively easy algorithm, and it doesn't have these black boxes and hidden ideas. So when I told ES, yes, but it is actually a big story to implement ES. So nothing is hidden here, yes, so it's very clear. So first of all, okay, so the quantum Fourier transform is just discrete Fourier transform implemented by on a quantum computer. And let me say what does it, let me shortly recall what does it do. The goal of Fourier transform is just to say that, okay, if I have a number, yes, so J, to create a signal of a frequency J somehow, okay, this would be J to the power, divided by 2 to the power n, yes, so which means that I create kind of periodic sequence, yes, with a proper, okay, it should be sinuses, but I put exponentials of complex numbers, yes, because I have to stay in something of absolute value 1. Yes, so but this is the way how it acts. Yes, so this is how I wrote it, yes. And okay, in that case, I define it in an element of a basis, yes, so then I can define it on the whole linear space, and okay, here I wrote the formula, I don't know what for, yes, but let us have it, yes. And the idea is that, okay, if capital N is 2 to the power small n, and this I will occasionally confuse them, so but this is actually then this is the matrix of this transformation. The good part of the story that this is a unitary operator, and by nature of quantum computers, it has to do unitary operators, but this means that this is of a spirit of a quantum computer. Yes? So there is a huge chance that we can effectively implement it because because Fourier transform is by itself a unitary operator. And okay, if you do discrete Fourier transform, it is a unitary operator in linear space. If you do Fourier transform in a Hilbert space, it is a unitary operator. So wherever you put it, it is a unitary operator. Yes. So this it's matrix. Okay, just as it is. Yes. But the true thing. So to create a scheme, I would like actually to do calculations in a quantum way of what is happening with basis states. Yes. So I have written here a formula before, but I would like to consider its different decomposition. Yes, so for this I need to replace k by a sequence of digits, which is here. And actually, okay, there is some calculations which you could check, but in the end, what is happening that this becomes a direct product. Yes, direct product of a states where 0 is always 0, and the reason is because if I put here k is equal to 0, then gk is 0, and so here is 1. Yes, so I always have coefficient 1 in front of 0. And whatever sequence of 0 and 1s I consider, yes, it would generate something not only consisting of not only of zeros, but of some other numbers as well. And okay, the proper way is just this direct product. Yes. And okay, let me admit why it is like this. Yes, and just recall that you believe me that it is true. Yes, and based on this equality, yes, I can show the scheme immediately, in fact. Yes, and the scheme consists of easier things. It consists of Adamar operators and phase operators. Yes, phase shift. Okay, not this is phase operator, not phase shift. Of phase operators. And okay, remember that we want to have like this. Yes. And this seems that, okay, given J, we just need to choose a proper rotation on a second coordinate on it. Yes? And when this coefficient is 1, yes, so we need to put 0 into it, so we need to create 0 plus 1. This is from where Adamar comes. Yes, actually. And okay, then, okay, here it is put proper way, yes, because if I consider basis state, so everything here is 0 or 1, I just need to understand to which each gate, each bit should be rotated on a proper angle, yes, and this is just a way to calculate proper angle. Yes, and I suggest that in a certain sense you trust me. Yes, and once again, and this is the thing. Okay, look. So I put here some L. Yes, and okay, all G which are how to say. So this G what was here. Yes, all the digits which are higher than L, number of digits. Yes, this would immediately kind of gives you 1. Yes, this part of this. So I consider J as a sum of G1 plus 2G2 plus 4G3 and so on. Yes, it will give you just all the digits which have indexes bigger than L will gives you 1. Yes, so this why this part is absent. Yes, and then okay, I need to properly put the things where it is 1 gives a rotation, where it is 0 don't give a rotation. This is controlled rotation, controlled phase operator. Yes, and okay, this is the scheme. Yes, and if it works correctly on every basic state, then it works correctly for all states, because the scheme is linear operator. And okay, so it works because we can do this for a single state. And question, what is about entanglement? Yes, as we tell that if we start with a basic state, the resulting state, okay, the resulting state is not entangled. Yes, it's a direct product. So what do you think? Does this scheme create entanglement? Or not? So can you start with a state which is not which is direct product, and end up with the state which is not direct product?
I'll guess.
No, you can guess yes or no. Yes. Which state?
I'll confess that this part is really complicated for me.
Yeah, no, you see, this is the problem. So if I show all the calculations, that each algorithm is more than one class, actually, yes, and we don't go forward. Yes, so I recommend actually everything to read in the books which I which I mentioned in the in this announcement of the course. Yes, it is very well written. Yes, everywhere there. Yes, but the calculations are there. Yes. Okay. So, but I ask another question, which actually is possible to answer with intuition, not with the formulas. Yes, and let me say that yes, it's possible And the reason is the following, like informal. If we don't do untangent states, we cannot get a computational profit. It is, as I mentioned, that this is the same as classical computers, but only instead of bits, you have real numbers. It is 0 and 1, you have a real number. We know that discrete Fourier transform is something of exponential complexity. Yes. So here, okay, I didn't calculate, but this is not exponential complexity. Yes, this is quadratic with respect to small n. So this is logarithm quadrat of capital N. Yes. So we gain exponential. We have an exponential gain in the speed. So somewhere entanglement has to appear. Yes, and okay, but another thing that the fact that basic states are going to direct products doesn't mean that superposition of basic states. So because what we say, superposition of basic states go to superposition of direct products. Come on, this doesn't mean anything. Yes. So the superposition of direct products is not a direct product. Yes, so this means that it creates entanglement. Yes, and yes, computational complexity. Yes, we have here n minus 1, n minus 2, yes, and so on gates, so n squared gates. And another thing, the good thing, that it contains only of simple gates. Yes, controlled phase. Yes, controlled phase. Yes, so there is nothing which we need to implement additionally. So you really have this. You can write gate QFT, I don't know, number of gates, and it will do this. What it actually is doing, yes, it actually considers 2 to the power n coefficients which stays in front of basis, and move them into another 2 to the power n coefficients. Yes, so from how you create the story that you have those coefficients, this is your business. This is outside of quantum Fourier transform. And of course, in general, yes, if you want just to have a classical sequence of numbers, yes, you need to upload it into quantum computer, which takes you exponential time. Yes, so you will not get a exponential speed up if you just want to use it as a classical thing. So what you should do, you just basically have to create this state by some algorithm. Yes, and this what is done. This is done in the case if you do it with inversion of linear operators. It's the story which you do with a Shor algorithm. Yes, so all of them, in their heart, they actually have how to create coefficients in front of how to create those fj. Yes, basically. Yes, and so it should be fk and this should be cancelled. So I wrote something crazy here. Yes, I should fix this. And this is the story. So I'm omitting what is omitted here is how you create the state. And I don't tell anything about what is happening after I applied quantum Fourier transform. It's usually also, something which you have to do. But let me show how it actually works. Yes. So how it actually works. Yes. So assume that I do 3-qubit. Okay. So this is an easy scheme which is implementing it. I think you cannot see it good, but okay, this is how it is. Yes, so this is just phase gates, controlled phase gates properly. And if I started with all zeros, yes, what should do the Fourier transform? It should give so if I was in a one basis state, it should give all the possible values with similar probability. And okay, it's doing this, You still need to test somehow what you are doing. Yes, and this is how it looks like when you run it on a real computer. So they're not equal probabilities anymore, but they look relatively similar. Yes, but it's hard to measure. Yes, what is equivalent, what is not equivalent, what is equal, what is not equal, because even if implementation is perfect, they should not be exactly equal. Yes, much easier is to say if I started, yes, with the state which is all of them was equal. Yes, then if I apply to them discrete Fourier transform, I should get pure state 0. Yes, and I first do 3 Adamar gates, which actually create a superposition that all the values are equally probable. And after this, I should get, like, and this is what it should be. Yeah, with probability 1, I should get all zeros. And this is what is actually happening. Yes, and actually happening is around 90%. Yes, so already on this scheme, on the stake of bits, I have 90% of success. Come on, this is very bad result, because I have here only 1, 2, 3, 4, 5, 6, 7, 8, 9 gates. Yes, 9 gates, and already I lost 10%. Yes, so if I have 100 gates, I lost everything, basically. And this is very simple scheme. This is, it doesn't contains fancy objects inside. Okay, this is the scheme which is actually round. Yes, so it's a bit longer. Yes, but still, it's not infinitely round. But what's happening? So if I do the same for 5 qubits, yes, and okay, I implemented it for 5 qubits, yes, and I get then that everything is possible here. And I go to get correct result with approximately probability 1/2. Yes. So this shows how far we are actually from real use of quantum computers. Yes. But there is one good thing, and this is good thing which I would like to stress attention of mathematicians, because this is our job to create algorithms which are stable with respect to these errors. If you look, so you have here, okay, there is a bunch of the other possible results. Yes, all of them are not correct. But you see that some of them are more probable than others. Yes. And okay, it's not visible here, but okay, I send presentation. We'll send presentation to everybody. Yes. Then you will see that these big error columns contains 1 and 4 zeros. So in a certain sense, it still remembers that the true answer is all zeros. Yes, because most of the thing it kind of get 5 qubits. 4 of them is 0 and 1 of them is 1. So mistake is in 1 qubit. And so this is a job for us, for mathematicians, to create algorithms which are stable with respect to such errors. Yes, because if our algorithms works good, not only when we get all of them 0, but when we get 4 of them 0, this would be, I don't remember, I think 80%, something like this. Yes, and increase from 50 to 80 is in fact not 8/5 increase. It's increase from 20%, from 50% error to 20% error. So it is kind of 2 times more effective. Yes, and okay, we don't have much time, so I will not start a new algorithm. So I will do this as a part of HHL. It was phase estimation. It was supposed to be warm up for matrix inversion. But I will show then another thing. I will show it not in presentation, but on a quantum computer. Yes, this would be the following. So let me consider the following. So first of all, I applied this, the Coulomb algorithm to create a specific state, yes, which is, so I used 3 qubits, and I created a 3 periodic state as much as I can do this, because 8/3 is not an integer, yes? So I put 1, 4, and 7. Yes, so concentrated on 1, 4, and 7 with equal coefficients. Yes, and this is the scheme how I did this. Yes, so first I used proper rotation to say that, okay, on the left there is 1, on the right there is 2. After this, I said that, okay, the right should be splitted. Yes, the left is 1, it should not be splitted. Yes, and choose the proper controlled things, yes, in the end, yes. So then what we should do, what should happen if we apply quantum Fourier transform? Yes. So we see 3 peaks here. Yes, theoretically, yes, in a perfect world, what is happening is that, so assume that we work not only with 2 to the power n sequences of lengths, but of arbitrary lengths. And assume that we have n, capital N, is equal to capital K times capital M. Yes, so assume that this is holds. And now assume that I take any k-periodic sequence. Yes, take k-periodic sequence. Yes, then quantum Fourier transform should, independently of what k-periodic sequence, yes, it should give me, as a result, a sequence which with support on on numbers which are how to say, multiples of n. Yes, so I will get a sequence by quantum Fourier transform. It should go to sum of some coefficient, yes, concentrated on Gm. Yes, which coefficient depends on which periodic sequence it was, and so on. Yes, but this is what would actually happen. Yes, and here, presuming that so this is the way how you can get from k-periodic sequence number m, because you measure this thing, and you get some multiple of m, which is a huge information about m. Yes, and this is what is actually a part of a Shor algorithm. Yes, so they create a periodic sequence, yes, by number theory, but now they need to find the period of this sequence. Yes, because this is the information which is actually needed to make a factoring. And the way how it is done is that they apply quantum Fourier transform and measure and get something which is most likely capital N over the period. Multiple of capital N over the period. And let us see. So capital N in our case is 2 to the power 3, 8. Period is equal to 3. What numbers should be the most probable? Yes, what is the most probable support? Yes, there. It should be 0. Yes, 0 times 8 to the power 3. 1 times 8 to the power 3, but this is not an integer. But what is the closest integer to it? It's 3. Yeah. And 2 times 8 to the power 3. And what is the closest integer? Is 5. Yes, 16 over 3 is 5. Yes, and if we look onto this picture, yes, this is a miracle. Yes, with the highest probability we have exactly 0, 3, and 5. So it very well, okay, this is a perfect, yes, so I didn't run it in a real computer, yes, but assuming that the computer is good, it really allows us to find period. Okay, in this strange sense, yes, so I can find some integer which is close to multiple of to such expression, yes. But in fact, because checking that an integer is a factor of this one is a fast problem, yes. So you get a guess, okay, you might be not correct, yes, a bit. Okay, it doesn't matter, yes, because you can do this very fast. But it allows in the end to create quickly good guesses, yes, to it. And so this is how it's inside Shor algorithm. I don't touch Shor algorithm because this is actually two lectures to give it complete and one more lecture to give explanation why it works. Yes, so because it's based on a not so trivial number theory, and in the end, it's also the implementation length of implementation for 15 is 5 times 3 is I cannot see it on the screen. Cannot show it. It's much longer. Yes, so but here it works, and you can play yourself. Yes, so I did it for 3 qubits here. You can do the same for 4 qubits, for 5 qubits. Yes, because quantum Fourier transform is implementable theoretically. Yes, and this Coulomb algorithm is also fine. Yes, but there I don't put here for more qubits because if you do Coulomb algorithm for more than 3 qubits, then you have to use controlled, not. Which is a controlled something, which is a long, if you just to open it, it's a long story. Yes. So okay, it is a good and complicated exercise because you can do this and the program is readable, but only you introduce new gates. Yes, you can introduce control 5 times. Rotation, how to say, and its implementation would refer to control 4 times rotation, yes, which would refer to 3 times rotation. You know, this is how to say, scalable. Yes, it's possible to do. You just to write a scheme for control rotation. I mean, this would be a very long scheme. It would be not readable. Yes, basically. So, okay, let's finish for today. Yes, the next lecture would be the last one. Yes, unfortunately, yes, I also think it's better to have mini course longer, but it's 6 lectures. And so there we will very briefly look on how to do. So I want to incorporate in the course at least one algorithm which could not be considered as a classical, so which is complicated. Yes. And I would and I choose this to be not Shor, yes, but the inversion of matrix. Yes, it's actually not inversion of matrix, but solving of linear equation. Yes, so basically it tells you the following. So you have a matrix U, and what means you have, you know, I meet, yes, and you have a state X. You have state X. This is your input. So, and you want to write a scheme which kind of, it starts with X, yes, and you do your scheme, yes, and it's end up with a state Y such that U, Y is equal to X. Yes. So this is what you want. And There are plenty of details, yes, which I would explain the next thing, because, okay, I formally can write it only for unitary a priori matrices, but maybe I want to solve not only for unitary matrix, yes. And if it is unitary, and it's implementable, why I just cannot do its inverse, so just to repeat the gates in opposite direction. So, okay, there are a lot of, so it's really useful algorithm. So please pay attention and please prepare to a hard mathematical lecture there, actually. And it would be mostly with Blackboard. Okay, so thank you very much.